Okay, let's talk about sensitivity. We're going to talk about system sensitivity and uncertainty. So what I'm talking about is parameter uncertainty, basically. Do you remember this picture? This is kind of the full enchilada for your MCSL. Well, back in week 2, you did a whole bunch of measurements, and at the end of that, you wrote a report, and it had 6 parameters: Ka, Km, Kp, Kt, N, and tau m. And what I asked you to do in that report is to comment on how uncertain you were of those derived parameters. Your Ka would have been negative 5.2 plus or minus 1%, 10%, 30%. The point wasn't to get a very accurate measurement of Ka. The point was to get you to think about the fact that you were uncertain about the thing that you were reporting. Not that it was wrong, but just that within the tools you used, there was some uncertainty about that number. And then we completely forgot about it for the rest of the quarter, and Ka was a number. Okay, now I'm going back to ask you to realize that, and it's not just Ka, it's like any resistor is a 5% resistor, 10% resistor, 1% resistor. Same with any component you buy, or make, or whatever, it's going to have some uncertainty in its fundamental parameters. So, wouldn't it be nice if we could quantify that and design around it? That's what I want to talk about today. So, one way to quantify sensitivity is how much uncertainty in a subsystem affects uncertainty in the mother system, in the larger system. Or you could go all the way down to the parameter. So when I say delta K on K, I want you to think of this like a percent uncertainty. Right, this would be 10% if K was a resistance. And this is uncertainty in the parameter K, measured as a percent, right? Because the units here cancel the units here. Then it's not too much of a leap to think that there will be some kind of uncertainty in the transfer function itself. Now, it's going to be less like a 10% resistor and more like the Bode plot is going to have some fuzz around it, or the pole zero map is going to have some uncertainty clouds around it. So it's a little harder to think about this in terms of percentage, but it is still an uncertainty. In the transfer function. And so what I would like to define sensitivity as is the scaling factor. So this quantity over here on the left, and again, I didn't come up with this notation, but this is capital S for sensitivity, subscript K for the parameter whose uncertainty we're mapping, superscript T for the transfer function to which we are mapping that uncertainty. Okay, in English, this is the sensitivity of T to K. This is the better way to say it. So, if we can look ahead as engineers, are we going to want this thing to be big or small? It'd be nice if it were small. That way a 10% uncertainty might become a 1% uncertainty. Or at worst, 10% becomes 10%. Nothing gets amplified. But it does kind of act like a game. Kind of, it is essentially a transfer function. Because at the other end of the line here, this is a function of S. And so if you want to be proper, this is capital S, a function of Laplace little s. Okay, I'm going to try and remember my serifs to indicate what's capital and what's lowercase.
I realized like those 10%, those percentages, are those like a probabilistic thing? So would it be, is there an implication that there's some distribution?
I mean, we're not implying any given distribution. What I'm saying, when I say that I know a resistor to within 10%, that leaves a lot up to interpretation. What I'm saying is that I know for certain it's between 1K plus 100 and 1K minus 100. Statisticians would then want to put a distribution on between 900 and 1100 ohms, but I'm not saying that. I'm saying I know for certain it's between 9 and 11, but I'm not telling you any kind of distribution therein.
So it's not like standard deviation?
No, it's much less informative than that,
Okay.
but also more broadly used, because who the hell does probabilistic studies on their resistors? I mean, resistor companies, I guess.
So this is just the uncertainty of one component in a transfer function?
Yes.
And then would we like add up individual components to the total?
You could do that, especially because it's going to act like kind of partial derivatives here. So you can talk about a total derivative. Or you could say, I have a transfer function. It is a function of two parameters. Which one is it more sensitive to? Let me spend more money and make that the less uncertain component. That's a very valid way to use this. Okay, so this is the general gist of it. Sensitivity maps uncertainty in a parameter to uncertainty in a larger function that is a function of that parameter. So if we do a little rearranging here, I'm going to take the sensitivity, leave it on the left, and I'm going to take the uncertainty in K, divide it over, and this is a fraction of fractions, which is probably better represented as the product of fractions. And so this is equivalent formulation of sensitivity. And what I'm going to do now is I'm going to say, let me, instead of talking about 10% uncertainty, let me talk about marginal uncertainties. And that is, take this finite delta t over delta k and make it a partial derivative. Okay, so this is now mapping for every marginal increase in uncertainty in k, what is the marginal increase in uncertainty in t? If everything behaves linearly, then there's no problem here. Like, you can just scale this up. But now I'm just saying, take this in the differential limit. So, and this is how I functionally compute sensitivities. So when you go to ask, is this transfer function more sensitive to k or to p? Do this for k, do this for p, compare the results. Okay, so for a given system, comparing two sensitivities within the system is one way to use sensitivity. Another way is comparing topologies. So that's what I'd like to investigate here. Which of these two ways to make a first order system are less sensitive to the pole location? Let's try and answer that question. So in the open loop case, what are we looking for? We're looking for the sensitivity of G to P. So that's the notation, which is partial of G with respect to P times the flip of that, P over G. All right. So partial G, partial P, is that easy or hard? Yeah. How should we do this? So G is what? K times P over S plus P. That might be a little easier. Fewer nested fractions. All right. So quotient rule sounds like the plan of action here. Low times the derivative of high minus high times the derivative of low with respect to P. Divide by denominator squared. And then don't forget P over G. All right. I got a K times P here and a negative K times P there. I've got an S plus P. One of those will cancel with one of these. This P will certainly cancel with that P. So let's neaten this up a bit. I get S times K over S plus P times 1 over K. All right. So, sensitivity of G with respect to P as a function of the Laplace S is this function. Is this good? Is this bad? Don't know. Sensitivities are less useful in isolation than they are in comparison. Okay? We'll talk about what this might mean in isolation in a bit, but I think the easier way to understand them is this sensitivity better or worse than this other sensitivity? Which is why we're doing this example. Any questions on this calculation?
So this sensitivity will change with different values of P?
Yes. Yes, so depending on the kind of nominal value of P, the sensitivity to that P will change. Because we're talking about marginal changes, so like a 1% change on a 10 rad per second pole might have more effect than a 1% change on a million rad per second pole.
Is it possible for the K to not cancel out?
It's possible that your uncertainty in P might be a function of other parameters. Yeah, I chose an easy one, so it didn't.
So then we like plot this as like a movie diagram?
That's where we're going. That's why it's in this unit.
Gotcha.
Yeah, exactly. It'll be less valuable as a function of S and more valuable as a function of omega. Exactly. Okay, let's do the closed loop. So we've got closed loop transfer function is KP over S plus P plus KP. That's right. So we're looking for the sensitivity of the closed loop transfer function with parameter Sarah. Okay, so partial T with respect to P times the reciprocal P on T. Let's go another quotient rule, methinks. So low times the derivative of pi minus I times the derivative of low with respect to P, which is 1 plus K. Don't forget, it's easy to do all the work for the partial derivative and then forget that you have to multiply the easy thing. Like I've done that a quart number of times. So this is then multiplied by P over our closed loop transfer function. It's just partial derivatives, differentiation. You've been doing this since Calc 1. I've done this a couple times, so I'm going through it kind of quickly because the differentiation is not the lesson here. Let's see here. This term, again, will cancel all of this. One of these will cancel that. There's a bit of repetition here. You're starting to see repeated themes. So we end up with S times K, divide by K, so I'm going to keep an S up here, and then S plus P So, can we, even before we go to the Bodhi plot, can we actually answer this question? This is a function of s. True. This is a function of s. True, but they have very similar forms. Yeah? For any positive k, p times 1 plus k is larger than p, which means this denominator will be larger than that denominator, and the numerator to match. So actually we can conclude straight away that the closed loop system is less sensitive to p. You would want that in a class about closed loop control, and it is true. But let's exercise our Bodhi legs anyway. So let's get this over here. This was the closed loop sensitivity. This was the open loop sensitivity. And we're going to look at the magnitude of the open loop sensitivity as a function of omega versus the magnitude of the closed loop sensitivity as a function of omega in dBs both. Which is why we need this to frequency response. Neither of these is in leading one's form. So let's make them in leading one's form to get some good old practice. This I've got to pull out of this entire thing, yeah? This is 1 over p times 1 plus k times s over s over p times 1 plus k plus 1. So this is a kind of a 3-ingredient Bodhi plot, masquerading as a 2-ingredient Bodhi plot. There's both a constant, a differentiator, and a real pole. Same story here, actually. It's just a little easier to factor out. All right. Thank you. That would have been really weird, but I have no idea where that happened. Yes. Okay. It'll be really difficult to plot these without some nominal values, and that's kind of true of any sensitivity plots. So let's take some nominal values. Let's do, let p be 100, and we'll let k be 1 for now. So we're going to need some frequencies on here. Let's put that as 1, let's put that as 10, 100 there. So let's do the bottom one first. The constant 1 over p is 1 over 100, so that's negative 40 dBs. And the differentiator comes up at 20 dBs per decade. Yeah. And the pole is 0 and then down at 100. Take a second, and please combine these into the resulting Bodhi plot. So the numbers work out pretty nicely. The differentiator is going to be moved down by a constant minus 40, which means now it crosses the negative 40 line at 1 rad per second, but it rises 20 dBs every decade, which means it gets up to 100 rads per second and 0 dBs. After 100 rads per second, we've got 1 positive, 1 negative, and 1 flat, which means flat in high frequencies. Okay. Questions on that? For the closed loop sensitivity, we've got a pole at 200 rads per second and a constant gain of 1 over 200. So I don't think it's too much to ask that we're going to look something like that. Because it's actually the exact same plot, except the P has been replaced. So everything that worked out nicely before will work out nicely again, except it happens at 200 rads per second. So, questions on that? If we were going to be operating this system, or if we're going to, the choice is between these two systems, and we were going to be operating it at high frequencies, does it matter? Not in terms of sensitivity. If we're going to be operating it in low frequencies, i.e. below the pole frequency, then all of a sudden, the closed loop system is less sensitive by 6 dBs than the open loop system.
So it just means that the sensitivity like caps out at 1?
Yes, that's another thing to recognize, is that neither of these will amplify sensitivity more than 1. Or amplify uncertainty more than 1. So these Bodie plots are nice and helpful when you have two sensitivities that you want to compare, but they don't compare as nicely as these two. It's pretty evident that this denominator was always bigger than this one, so this one's going to outperform this one.
So you could have two Bodie plots that aren't necessarily more or less sensitive than each other. It just depends on your region of operation.
Yes. Yeah, that's another thing to recognize, is that, right, so truly these are functions of S, but we functionalize them to talk about at what frequency of operation you're planning to use it at. Wait.
So are you saying the yellow is more sensitive to low frequencies because it doesn't attenuate as much?
Right. The open loop system, the yellow system, is more sensitive to uncertainty in the pole frequency when operated at low frequencies than the closed loop system. That would be the one sentence conclusion of this lesson. Okay.
So I should think of like that sensitivity is it's kind of weird to think of sensitivity as a transfer function, I think.
But it does transfer something to something. It transfers uncertainty in a component to uncertainty in a system. Just like transfer functions transfer inputs to outputs. But it's it is a little meta to wrap your head around.
Since K is only impacting the closed loop transfer function, then the sensitivity could actually be worse in the closed loop system if K were like a smaller value, if you were to adjust that.
Yeah, that's a good point, is that we kind of glossed over the fact that the closed loop sensitivity is a function of K. But as long as K is bigger than 0, we'll still get this relationship where blue is under yellow, but the gap will be a function of K, for sure. Good. All right. So let's kind of zoom out a little bit, but this still uses the same same terminology. So, if we talk about a unity feedback system with a controller and a plant transfer function, then I don't have to talk about the sensitivity of a transfer function to a component, to a parameter. I can also talk about the sensitivity of a transfer function to an entire subsystem. And so that's what this S sub C sup T is. This is the sensitivity of the closed loop transfer function to the controller transfer function. It follows all the same math that we did before. In particular, I'm taking the partial of the closed loop transfer function with respect to the controller, and then I'm multiplying by the controller over the closed loop transfer function. And we get this somewhat familiar result. So I say somewhat, because I haven't actually harped on this too much. We haven't much talked about it since the steady state error chapter. But if you do a separate analysis, and maybe you remember this from the steady state unit, if I take the error as the reference minus the output, then the reference times 1 minus the transfer function, closed loop transfer function. If I write the 1 as 1 plus CP over 1 plus CP, then the transfer function is this, and I just get 1 over 1 plus CP. Again, it goes by a couple names. It is the sensitivity of the closed loop system to the controller. It is also the transfer function of reference to error. For unity feedback systems, they're the exact same thing. And for this reason, because it holds this property, this is actually just called the system sensitivity function. And this is a bit confusing because I'm laying all this on you in under 30 minutes, but we can talk about sensitivity of T to a parameter. And in the next breath, we can talk about the system sensitivity function. They're rooted in the same thing, but this is a bit more generic, a bit more general. I'm kind of stoked that we're going to get to this, because we don't actually usually get to this in 302. But stop me if you need help along the way. Compare the sensitivity function with what's called the complementary sensitivity function. Complementary in the sense that they sum to 1. So if I take the sensitivity function and I add it with something, I get 1. That one thing is CP over 1 plus CP, which is the closed loop transfer function. So this is known in some circles as the closed loop transfer function. It's also known as the complementary sensitivity function. You don't have to abandon CLTF. You can still think of it as a closed loop transfer function. But for the next 50 minutes, I think it would be helpful to think of these two as being complements of each other. These are functions of S. This is not. This is a constant. So, I want you to think that if I make one small out of a particular S, I have to make the other one bigger, or vice versa. I can't, in general, make them both small or make them both big. They have to sum up to 1 because of how they're defined. So, what are the implications of that kind of innocuous statement? Let's look at a pretty generic closed loop system. It's got a controller, it's got some disturbances, it's got a process. It's even got an output. Look at that. It's also got sensor noise. Let's treat all of these sums as positive, except for the feedback. That'll be negative, as is custom. So the transfer function, so 3 inputs, 1 output. 3 transfer functions. Each of them claiming to be the closed loop, a closed loop transfer function, right? They both, or all 3, appear as inputs, and on their face, none of them are different from the others. They're just coming in at different points around the loop. Some of them aren't even coming in at different points around the loop. Right? There are those of you out there that see this summing junction, and want to make them one summing junction. So let's talk about these various closed loop transfer functions. Okay, from R to Y. That's our classic, right? That's the one we're talking about all 4. That is our T of S, either the complementary sensitivity function, or if you like, CP over 1 plus CP. How about N to Y? Here is where viewing these as merged might make a little sense. If I take this negative sign and I back propagate it, it becomes 2 negative signs and then a positive sign. If I propagate this negative sign, it can become its own -1 block here. And then this signal enters this system just the same as R did. So, negative T of S. And then from disturbance to output, well, if you kind of tilt your head, now P is forward path and C is feedback path. And I can pop this negative sign down the line, and I get P over 1 plus CP, which you can also now write as P times the sensitivity function S. Questions on that? So if I want to talk about the output, what I'm really talking about is, according to superposition, the output due to R plus the output due to D plus the output due to N. In general, all 3 of these might be active at any given time, so I have to account for all of them. So the output can be written as the output due to R, which is the R to Y transfer function times R, plus the output due to D, which is the D to Y transfer function times the input D, plus the output due to N, which is the N to Y output transfer function times the input N. Okay. That's all well and good, and we've got pretty sweet abbreviations for all of these fractions just up here on the top of the board. What I want to talk about now is a little bit of a curveball, but I want to, rather than talking about the output, I want to talk about the error. Because the behavior of the output changes based on the shape of the reference signal. So that means that you can never talk about, oh, is this output good? You have to say, is this output good given a reference signal of blah? If instead you talk about the error, you can just say, I want the error to be small. And that's true regardless of the shape of this function. Okay? So the error will still be the output minus the reference. That was our definition from back in the day. But this output is now the sum of all three of these inputs. Sorry, outputs. Okay, so the first one, the R to Y transfer function, that was a complementary sensitivity function times the reference. The second is the D to Y. That was the T of S times the sensitivity function times the disturbance input. The third is, well, I guess minus now, minus the complementary sensitivity function times the noise process. Minus R. So all of this is Y. I go off screen again. Christian, where were you on that?
Oh, sorry. I was too focused there.
Yeah. Yeah? Okay. I inconveniently placed them at the opposite ends of the expression, but I want to focus on this and this. That is a factor in R out. That's T minus 1, which is sensitivity. Okay? So, in summary, the error in our system is a function of this disturbance times the sensitivity function times the plant transfer function. It's also a function of the noise times the complementary transfer function. Sorry, complementary sensitivity function. And it's also a function of the reference times the sensitivity function. Cool.
Isn't T minus 1 the negative sensitivity?
Sure. I'm going into Bodhi land right now where I'm going to take magnitudes. Yeah. But thank you. Right, if I'm talking about error, I'm probably going to be talking about magnitude of error. If I'm 1 degree above or 1 degree below, in most contexts, that's 1 degree of error. Okay? Check this out. Remember what I said about not being able to make T and S small simultaneously? What are the ramifications of that here? I can either reject noise by making T small, but by doing that I have to make S big, which means that my reference will introduce error. Or I could make S small, which means my error due to a reference change will be small. But if I have noise, that will have to be, the effect of the noise will be big, in kind of broad strokes. The disturbance kind of lives in a middle land, where it's a function of both the sensitivity and the plant. So that's why I'm kind of ignoring it, because the most obvious conclusion is the battle between these two terms. Is I can't make it good for both. But maybe I can make it good for some frequencies here and some other frequencies here if we go over to Bodie land. Let's go there. So we have the result for the relationship. It's the sensitivity and the complementary sensitivity must always sum to 1. So this is a little strange because I'm going to talk about them in dBs, and I'm talking about their sum here. But certainly, if one of these is close to 0 dBs, the other one has to be very small in terms of dBs, and vice versa. So, what have most of our closed loop transfer functions generally look like in the frequency domain? Low passive. Closed loop transfer functions have mostly been steady DC gain and then falling off. They might have some resonance, but they're going to generally fall off. So maybe this is T. And if I know this, if this guy gets small, this guy has to be close to 1. And if this guy gets small, this guy is close to 1. So this is magnitude S. In the middle here, it's kind of muddy, but let's focus on the easy bits first. So this is kind of like just the average closed loop transfer function we've seen has had this kind of behavior, which tells us what about noise rejection? By and large, our closed loop systems reject noise at high frequencies. That's kind of sweet. We didn't even try to get that. And conversely, where is the sensitivity function small? It's small at low frequencies, which means if your reference signal doesn't change much, you can actually reject error due to reference as well. So, I think this would be actually a great way to end the quarter, but I have 3 more hours to teach you stuff, because this is a bright note. Without really trying, we got kind of low frequency rejection tracking and high frequency noise rejection for free. Not for free. We worked for 9 weeks for this, but I don't know. I kind of like that. The sticky wicket is a disturbance. I'm going to talk about that. It also plays a role, but it doesn't play nicely like these. So, sorry. Can't really let anything go with a true happy ending. Have a great weekend. See you Monday.